Welcome back from the previous video where we discussed what a vector is and some basic properties. In this video we'll move on to discuss some basic operations with vectors, including addition, scaling, and subtraction. So first, for addition, if I have my vector A and I want to add another A to it, we can look at this graphically and algebraically. So graphically, what I want to do if I want to add these two together is I take another vector and add it tip to tail, and my resulting vector, call it B in blue here, is from the tail of the first to the tip of that second vector that we added. So that's the sort of the graphical process that you can use anytime you want to add two vectors. And if we want to look at this algebraically, we could do this by just adding each component of the vector. So we could say our vector B, which is equal to our vector A plus our another vector A, is equal to 1, 2 plus 1, 2. And in order to add these algebraically, we just combine and add those x components together and add those y components together. So pretty simple here. We've just got 1 plus 1 for the x component, and 2 plus 2 is 4 for that y component, resulting in this vector 2, 4, b. Now, it's sort of another way you might want to think of adding two vectors. Let's say we have our first vector A. We're going to go over 1 and up 2 for that vector. And then we add another vector A. We're going to go over 1 and up 2 again. So if we want to think of their addition, instead of making that 4 steps, we could just kind of add those x component steps together and those y component steps together. So we're just going to take 2 steps over and 4 steps up, and that's how we add. And notice that we could also express B as just a scalar of A. So if B is equal to A plus A, we could just say it's equal to 2A. And the way we could show this algebraically, we just put the 2 out front of our vector, and when we make that operation, we're just going to multiply that 2 by each of those components, the A1 and the A2 components of that vector, giving us 2, 4. Similarly, I could scale it to a half. So say we have a new vector C, and it's going to be 1/2 A. So we just have the 0.5 out front and multiply that by each of the components, and that gives us the vector 0.5 and 1, which would look like this. So in either of these cases, B and C, they're going to be what we call scalar multiples of A, and something we'll see quite often in multivariate calculus. And something to note here with scalar multiples is that no matter how I scale this, no matter what I make that coefficient, whether it's 2 or a half or whether it's negative, the vectors are going to be parallel. So we can say that all scalar multiples of a vector are parallel. And notice that this doesn't require any information about the starting point either. If I started at 1, 0, that's still going to be parallel as long as it's a scalar multiple. Alternatively, you can imagine a vector like D, which is equal to the components 3 and 1, is not going to be parallel to A or any of these other ones. And to add a vector like this, we still basically do the same exact process. We just go tip to tail, and a resulting vector starts at the tail of A and ends at the tip of D. So we can describe this algebraically as E is equal to A plus D. So we have our 1, 2, and we add that to 3, 1, and we just add those together and we get 4, 3. All right, we can do something pretty similar if we want to subtract these. So let's just say a new vector, we'll call it F, and it's equal to A minus D. And so algebraically, instead of adding these components, we just subtract them. So we'll take our 1 minus our 3, gives us -2, and our 2 minus our 1 gives us 1 for our y component. And graphically, we could think of this as F is equal to A plus -D, where we know that our -D vector is the opposite scalar multiple of our D vector. So we just use that same process of tip to tail. We take that -D and add it tip to tail to A to get our subtracted vector F. So that is subtraction and addition. And to summarize, we discussed what a vector is, some uses of it, applied some basic properties of it, including the magnitude and direction, and we've classified some geometric relationships, including them when vectors are equal or parallel. And we'll move on to the next video into 3D, which we'll be dealing with primarily in multivariate calculus, and which is fitting because we do live in a 3D universe, so a lot of applications there in 3D. So until then, take care.